Okay, so let's go for an interesting test. We are going to pick a grid from Spain, France, and I believe Portugal that comes from the ENTSO-e transparency platform. And this grid was used by RTE to demonstrate the net transfer capacity in a workshop in the Linux Foundation back in September 2024. So these are the CGMES files. So this is the boundary, this is Spain, France, and Portugal. And next, what we're going to do is to launch the version of GridCal that I have here in the system. All right, now we have it. So we just need to drag and drop the files onto the user interface, and it will start reading and unpacking and making sense of whatever it's in those files, which turn out to be CGMES. Let's close this for now. So this is telling us that the grid is too large to produce an immediate schematic of the whole thing. Do you want to continue to produce a schematic? Let's say no, because I know that there are no coordinates either, so it's not going to be very productive. And next, because this is CGMES, GridCal is going to show you a special window called Rosetta. And it's already telling us that there's a lot of stuff that it doesn't like. So this window is special for CGMES. So since we loaded this format that comes from the common interface modeling, we can use this window to see what was in those files, right? In the same language that was in those files, which is this CGMES, the European Exchange Standard. And all right, so there's something, there are objects in here. All of these objects were found. And then if we go to the logger, we see that there are error warnings and some information. Let's see the errors. So there are objects that are missing properties, some classes that are not recognized. Well, this is not too bad if we inspect resource owners, resource share. Well, we could implement this in the future. Then there are many loads with exponent model. I believe that's not handled yet. There's conducting equipment missing from the terminals. This doesn't sound great. Plenty of errors like that. Then length missing, probably in lines. Also not great. That could be a pretty big error indeed. And then warnings, generating units with p equal to 0. Well, and a bunch of other errors like regulating condition equipment with no control, something called acceptable, I don't know what it is. No tap changer control from radio tap changer, yeah. Well, and something is that the HVDC was detected. Huh? Okay, so we can close this window, and then the CGMES model has been already fully converted to GridCal, so we can discard this information. And we do not have a diagram, but we can see what was converted here in the database. So we do have substations, voltage levels, bus bars, connectivity node, buses, switches, lines, all the thing, right? Let's see if we have technologies. Yeah, we do have technologies. That's all right. We have plenty of information, loads. So the next thing that I do right off the bat is to run this stuff, the sigma analysis. The sigma analysis is a very nice thing that comes from the holomorphic embedding line of research, let's say, and it essentially tells you if your voltages are or not in collapse, and if they are not, how far from collapse they are. And this is a fully static analysis, but it's a very good proxy for this information. So it is already telling me that the sigma coefficients did not converge, sad face. And we get these dots, which come in yellow and red. Yellow and reddish colors means it didn't converge, but if it was blue or greenish, then it would have worked. So this is not helping us too much. Okay. This is already a terrible sign if this doesn't give you any good information. So we can go to the power flow settings and try to use Newton-Raphson, just a good old Newton-Raphson. We will retry if fails. We will ignore the islands. We will apply the generator control limits. And we will use the voltage guess. This is, if you want, the power flow to start from the voltage solution that came with the file. That voltage solution is possible to see in here in the buses. You will see this, VM and VA0. These are the voltages that, for whatever reason, were obtained. And let's try to run a power flow. All right. So from here, we can see that there's some voltages, some angles, loadings, and whatnot. But something else that I always look at is the logs. And oh boy, there are logs. Try solution is garbage. This is telling me that it try first Newton-Raphson, then Powell-Dirichlet, then holomorphic embedding, then Iwamoto, and then Lerber-Marquardt, and none of those got a good solution. In fact, all of them stay in the range of 1 to the power of 4 error, and that's really, really, really bad. In fact, here it's telling me that the Jacobians are singular. By the way, a singular Jacobian indicates that we are unequivocally in voltage collapse. So, did not converge even after retry. Okay, but still, we can plot the voltages and see at least if we like the voltages we see. Well, yeah, you know, they kind of look good. Well, not terrible at least. These ones going to 125 are not great. This one below 190, 090 is not great either. But you know, something else that I do is trying the linear AC. This is a fully linear with voltage module approximation as well, not only the angle. So let's try this one, and let's not retry because we already know what's up, and not use any voltage guess here. So if we run this, alright, some voltages around 1, and we see this stuff. Some places are almost going down to 0. This is probably the most problematic thing that we see. However, if we discard this one and zoom this area, you know, something, some voltage. But can we trust this? Definitely no, we cannot trust this information whatsoever. And the last thing I do is to go to this tool, the data analysis tool, and it's going to give me hints of what's possibly wrong. So there are plenty of things that the program is looking for, and we already see that many of those occur, such as noise acceptance, reactance too low, the transformer rating is different from the nominal power, but this is not bad for power flow per se. Tap modules too low, so if we make this larger, we see indeed transformer taps that look a bit low. Some resistance is equal to exactly 0, this is not great. Some of these are from Electrica, and this type of encoding is from RTE for sure. Well, there is no, well, usually transformers are modeled without reactance, but yeah, if you really want to model properly, they should have also resistance. This one is especially worrying, right? The large nominal voltage mismatch. This means that there is a transformer with a certain voltage connected to a bus with a certain nominal voltage, and the two voltages differ too much. Usually a 10% is allowed, but these ones go up to 12%, not really too bad, but 12%, 15%, almost, almost 19%. All this is signaled. Even though there's difference, it's not like an outrageous difference here. The short circuit value is suspicious. Usually, transformers have a short circuit value of around 20%. So this, well, could be, 20 something. Yeah. This certainly, suspicious. This 94%, definitely not possible unless you made your transformer out of plastic or wood. This doesn't exist either. So all of these are data smells, stuff that probably tells you that this is modeled with incorrect information. And the last thing we are going to do, of course, we could hit this button, fix issues, and this will try to put everything that's out of range in range. Sometimes that helps, but I already tried, but this is not going to help you too much. So let's leave it as it is. The last thing I want to show is if we go to model and then compile arrays, this section is something I developed years ago just to help me debug models easily. And if I hit the calculator, it will tell me here the number of islands, topological islands found. And there should be at least one. But in this case, it turns out that there are 4,703 islands. Probably most of these islands are single buses. It will worry me if there were many islands with more than one bus. So this one is probably the main island. So let's hit the second one. One, and probably like that, huh? So many buses that are not connected to anything. That's not great either, but GridCal handles that. So every time there's a single bus that doesn't have a generator connected, that bus is ignored. And this is pretty much, but something else that we can do is inputs analysis, and then we see if this is balanced at all. So if we go to the inputs analysis, we do some zone analysis, yeah, there's a substantial difference between generation and load. Huh? and the countries don't seem to be properly matched either. But per area, the areas are properly assigned. So at least per area, there's a really massive difference in here. Yeah, this doesn't look great. Well, this is all for now. There are a lot of utilities to say if a model is correct or not. After this initial analysis, I can unequivocally say that this model is not correct. There should be a lot of actions being taken for the data to be correct.